cs407 Numerical Analysis, Section 3.2, Newton's Method. This procedure is also known as the Newton-Raphson iteration, and there are more general forms than the one that we'll see here today. In any case, this is one of the most important procedures in numerical analysis. In this section of the text, we'll look only at a single equation to find its roots, although we'll see some applications where you can have more than one. So, basically what we want is we want a root of a function f, somewhat like we wanted with the bisection method. And now our assumption is going to be that f is differentiable. So the graph of f has a definite slope at each point, and hence a unique tangent line. That's what it means to be differentiable. So at a certain point, x0, f of x0, on the graph of f, there's a tangent, which is a very good approximation to the curve in the vicinity of that point, some epsilon neighborhood. It's a very close approximation. So what we'll do is we'll label that with the script L again, and the script L of x is f prime of x at x0 times x minus x0 plus f of x0, and that's going to be very close to what the function f is near x0. Anyway, at x0, the two functions L and f agree with one another, at least within that epsilon neighborhood. We can take the 0 of L as an approximation of the 0 of f. And now we can find the 0 of L using x1 is equal to x0 minus f of x0 divided by f prime of x0. So we start at x0 as an approximation and proceed to the new point x1. We then iterate, and basically we'll get x2 is equal to x1 minus f of x1 divided by f prime of x1. x3 is x2 minus f of x2 over f prime of x2. And under favorable conditions, the sequence of points will approach a 0 of the function f. So here's the geometry of Newton's method. This is figure 3.4 from page 126 of the 7th edition. So again, we have the line y is equal to L of x, and that line is tangent to the curve y is equal to f of x, which is the blue one there. Now notice it intersects the x-axis, the tangent line curve does, at point x1. And the slope of L of x is f prime of x0, which is where we took that derivative right there. And that will give us the slope of the tangent line on that curve, which is a classic definition of a derivative, but here is the geometry. So you can see x1 is going to kind of fall close to the root, and we can do this again and again to get closer to the root. Well, another interpretation is, suppose again that x0 is an initial approximation to a root of f. Want to know what correction h should be added to x0 to obtain the root precisely. In other words, f of x0 plus what h is equal to 0. Now, if f is well behaved, then we'll have a Taylor series at x sub 0. Now, we have this Taylor series for the function, but finding h here is not going to be easy. Therefore, we give up the expectation of arriving at the true root in one step, and seek only an approximation to h. So we can get this approximation by ignoring all but the first two terms. So here x1 is equal to x0 plus h, which gives us the formula x1 is equal to x0 minus f of x0 divided by f prime of x0. In retrospect, we see that the Taylor series was not needed after all, because we only used the first two terms. In the analysis to be given later, it's assumed that f double prime of x is continuous in the neighborhood of the root. This assumption also enables us to estimate errors in the process. So this leads to a recursive inductive formula. If Newton's method is described in terms of a sequence x0, x1, etc., etc., then we can use the following recursive definition. Xn plus 1 is equal to xn minus f of xn divided by f prime of xn. So naturally we'll be interested in whether there's some limit as n approaches infinity of xn conforms to some r, where r is the desired root. In the meantime, let's content ourselves to look at an example. So, here we have f of x is equal to x cubed minus x plus 1, and x0 is equal to 1. What are x1 and x2 in the Newton iteration? Well, here we simply use the formula. So, x1 is equal to x0 minus f of x0 divided by f prime of x0. That's our formula, and f prime here, we take the first derivative, so bring down that 3 and lower the exponent by 1, 3x squared, and the derivative minus x is 1, derivative 1 is 0, so the final derivative is f prime of x is 3x squared minus 1, and so we can evaluate f prime of 1, which is 3 minus 1, 2, and f of 1 is 1 minus 1 plus 1 is 1. So x1 is 1 minus 1 over 2, which is 1/2. And now we simply repeat for x2, and we again find that we again evaluate at x1, f of x1, and f prime of x1, and our result is we get x2 is equal to 3. So let's see, now that we've seen how it works, let's put it together in some pseudocode. And here's the pseudocode from Newton's method from the text. Now, using the initial value of x as a starting point, we carry out a maximum of n max iterations of Newton's method. So that gives us an upper bound on how many times we're going to carry it out. We're also going to pass it the external functions f and f prime. And again, we have to define those because we don't have the symbolic way of taking the derivative. Later on we'll see numeric ways of taking the derivative. We pass it epsilon and delta, which are used to control the convergence and are related to the accuracy desired or the machine precision that we might have available. So again, one of the important things is you have to supply the derivatives and the external function, and we proceed with Newton's method by taking those ratios and subtracting them. So let's see how this works. We can use this procedure, and I've written the code for this, to locate a root of x cubed plus x is equal to 2x squared plus 3. Now, subtract the 2x squared plus 3 from the left-hand side, and f of x is x cubed minus 2x squared plus x minus 3. And let's start with x0 is equal to 3. Now, f prime of x is going to be 3x squared minus 4x plus 1. And I took the liberty of coding this up tonight rather than just copying the results out of the book. And my version works pretty well. Here's the results. So you can see after about 6, this converges to 2.17456, and that's actually pretty close. Notice that you get a doubling in accuracy in f of x and also in x until the maximum precision of the computer is encountered. So you get doubling of precision at each turn. I didn't do enough decimal places to see it in some of the further ones, but you can see that f of x doubles in terms of its precision each time. So here's a figure that shows a computer plot of 3 iterations of Newton's method for this sample problem. Again, the function is given by the blue line. We take the derivative at the point 3 and derive the slope at the tangent line, draw the tangent line down, and we derive 2.4375 as where it intersects the x-axis. Again, we evaluate the function at that point and evaluate the derivative of the function at that point, find the tangent line, slopes down, and we get about 2.21303. Now, using mathematical software that allows for complex roots such as MATLAB or Maple or Mathematica, we find that this one has the single root of 2.17456, which is what our little program got, and a pair of complex conjugate roots of 0.0872797 plus or minus 1.17131i. And in general, the numbers work out pretty well. So this thing converged pretty darn fast, and the number of correct figures in each step of the answer is nearly doubled. So 5 or 6 steps of Newton's method often suffices to yield full machine precision determination of the root. And there's a theoretical basis for this dramatic performance, and that's the theorem of Newton's method, and we'll take a look at this. This gives some conditions here. Now, so if f, f prime, and f double prime are continuous in the neighborhood of a root r of f, and if f prime of r is not equal to 0, now it's important, then there is a positive delta with the following property. If the initial point in Newton's method satisfies r minus x0 is less than some delta, then all subsequent points xn satisfy the same inequality, converge to r, and do so quadratically. So we get that doubling of precision each time. That is, r minus xn plus 1 is less than some function c of delta, which is the error relation, times r minus xn, the previous term, squared. And the formula for this error relation can be found under equation 2 on page 130. So, a little more discussion on Newton's method. In the use of Newton's method, consideration has to be given to the proper choice of starting point. We'll see some pathological examples there where it blows up. Usually you have to have some insight into the shape of the graph of the function. Sometimes just sketching a coarse graph like some of the ugly ones that I do on my solutions to the labs is adequate, but in other cases a step-by-step evaluation of the functions that function at various points may be necessary to find a point near the root. Often several steps of the bisection method are used to initially find a suitable starting point, and then we use Newton's method to improve the precision because it goes much faster. So, although Newton's method is truly a marvelous invention, its convergence depends upon hypotheses that are pretty difficult to verify a priori. So some graphical examples can show what can happen when we get pathological cases. And here are 3 failures of Newton's method. And again, it's important to pay attention to the starting point. In the upper left here, the tangent of the curve of the function f at x0 slopes to a remote point r. Successive points are away from r. Here's r that we want, and the tangent line actually slopes away from it, and successive iterations slope even further away. This is called a runaway. So the successive points recede from r rather than converge to it. In the upper right, the tangent of the curve is parallel to the x-axis, and x1 is going to be plus or minus infinity, or gets assigned machine infinity in the computer. Anyway, this one's going to end badly. And finally, the lower figure shows iteration values that cycle between 2 different numbers, x0, x1, x2. And x0 is equal to x2, you can imagine x3 is x1, etc. So they cycle back and forth. In a computer, the round-off error limited precision may eventually cause this cycle to become unbalanced, and you might get lucky and it might converge, or it might spiral outward and diverge. You don't know, and so that's kind of a pathological case as well. And finally, the case of multiple zeros. The analysis in the theorem establishes a rather troubling hypothesis that I said was going to be important. F prime of 0 is not equal, or F prime of r is not equal to 0. If F prime of r is 0, then r is a 0 of both f and f prime. This is called a multiple 0 of f. In this case, it would be at least a double 0. And Newton's method for multiple 0 converges only linearly. And one of the problems is ordinarily you don't know in advance that the 0 sought was a multiple 0. So, what can you do? Well, if we knew in advance that the multiplicity of the 0 was n, then Newton's method can be accelerated by modifying the equation to read xn plus 1 as xn minus m, which is the multiplicity of the zero in question, times f evaluated at xn divided by f prime evaluated at xn. The multiplicity of the zero r is the least m, such that f of the kth derivative of r is equal to 0 for k less than m, but f of m, the mth derivative, is not actually 0. And you can see a couple examples of these functions with more than one zero on page 131 and 132 of the text. So, for example, here p2 is x squared minus 2x plus 1. And we kind of know that's x minus 1 squared. So it has a root of 1 with multiplicity 2. And p3 is x cubed minus 3x squared plus 3x minus 1. And that's also x minus 1 cubed. Now, when we plot the curves, we see both curves are kind of flat down here at their roots, which slows down the convergence of the regular Newton method because we're interested in the slope of the tangent line. Also, the figures illustrate the curves of two nonlinear functions with multiplicities as a region of uncertainty about the curves. So, the computed solutions could be anywhere in the indicated intervals of the x-axis, which pretty sizable in some cases there. This is an indication of difficulty in obtaining precise solutions of nonlinear functions with multiplicities. Another application of this is for systems of nonlinear equations. So some physical problems involve the solution of systems of n nonlinear equations and n unknowns. One approach is to linearize and solve repeatedly, and this is the same strategy used by Newton's method in a single nonlinear equation. Not surprisingly, you can do this as an extension of Newton's method, and it does require some familiarity with matrices or inverses and partial derivatives. But it is an application of Newton's method, and if you're interested and you've done some of the math like Math 301 or 302 here at UH Hilo, then you can take a look at pages 132 and 133 of the text. Another cool application of this is to use Newton's method to find complex roots by programming it to work with complex arithmetic. And this is some of the frontiers in numerical methods and nonlinear dynamics. So what we have here is a fractal picture, and these can be created pretty easily with the help of Newton iteration. So basically we have some nice interwoven sets in the complex plane. They're quite beautiful when you put them into color on the computer, and these are fractal basins of attraction. So what we start out with is we begin with the polynomial in the complex variable z. For example, p of z is z to the fourth minus 1. That's suitable. Now, that polynomial has 4 zeros. Now, because we have z to the fourth minus 1, those are going to be the 4 roots of unity. So it's the roots of unity for a complex number, or any complex number that gives 1 when raised to some integer power n. So 1 raised to the fourth gives us 1, minus 1 to the fourth 1. I to the fourth gives us 1, minus I to the fourth gives us 1. Now each of these zeros has a basin of attraction. So there's a set of all points z sub 0 such that Newton's iteration started at z0 will converge to that 0. So these 4 basins of attraction are going to be disjoint for these 4 basins of attraction are disjoint from one another because if the Newton iteration starting at z0 converges to 1, 0, then it can't converge to another. It's going to converge to only one of those 4 zeros. And basically we'd expect each basin to be a simple set surrounding the 0 in the complex plane, but they actually turn out to be far from simple, and given that you're starting with 4 points on the unit circle in the complex plane. So, to see what they are, we can systematically determine for a large number of points, take a point and determine which 0 of p the Newton iteration converges to if started at z0. Points in each basin can then be assigned different colors. And there are going to be some points on occasion that don't converge, and we can leave those uncolored. So we'll finish off here with a plot of z to the 5th minus 1, which is in which 0 is represented by the color black. And this is from Jan Homan, who placed in the common domain Wikimedia Commons, and this was made with Mathematica. So you can get really neat and beautiful graphs using Newton's method in the complex plane as an application. Anyway, the next time we're going to look at the secant method, and it's a general purpose method, and it's nearly as fast as Newton's method, so we'll find it useful.